All right, for problem number 10, function g, again, we're doing the same thing as the previous one, figuring out all of our information that we would need to graph it and then actually graphing it. So the first step for this is going to be the same as the last one, finding the vertical and horizontal asymptotes. So what you want to notice here is that these are cube root functions because they have denominator 3 in their powers. So cube root function in general doesn't have any issues with the domain, right? There's no number that you could plug in here and not be able to take the cube root of it. So that should clue you in that there's no vertical asymptote here. A vertical asymptote is some number that when you plug it in for x, you don't get an answer, and then that its limit would tend to infinity. In this case, the domain of this is all real numbers, so there can't be any vertical asymptotes. Horizontal asymptotes. This is not a fraction, so you can't use any of your degree comparison rules. So instead, we have to do the actual definition of horizontal asymptote, which is just taking the limits at infinity and negative infinity. However, x to any power, if x goes to infinity, that term goes to infinity. This is not converging to any number. Same thing with negative infinity. This would just go to negative infinity. So there's no horizontal asymptotes either, because as you approach infinity, it just keeps getting bigger or smaller on the left. So we have no vertical asymptotes, and we also have no horizontal asymptotes. Again, vertical asymptotes was, is there any parts that, any numbers that are not in the domain that would have a limit that goes to infinity? Can't have that because our domain's all real numbers. Horizontal asymptotes is take the limits of these as they go infinity to and negative infinity, and do they approach any specific number? No, they don't, so we don't have any horizontal asymptotes either. All right, so for part B, we're finding critical numbers, increase, decrease, and concavity. So we need to take our derivative. So g prime of x, our derivative here, we can get just by using the standard power rule across these. So the derivative of x to the 2/3 would be 2/3 x to the negative 1/3. And the derivative of 2x to the 1/3 would be, you'd still have the 2, and we're bringing the 1/3 down, so that actually also has a coefficient of 2/3. And our power on that one would be x to the negative 2/3. All right, so in order to find the critical numbers of this, we need to combine these. And the reason we need to combine them is since these have negative powers, these are now fractions, and we need to combine them using a common denominator to be able to tell when this is equal to 0. So what I'm going to do first is factor out the 2/3, and then we'll deal with what's inside. These both have 2/3, so I'll take that out. X to the 1/3 is 1 over x to the 1/3. And x to the negative 2/3 is 1 over x to the 2/3. So in order to combine those, we need to get a common denominator. But since these are just x's with different powers, the common denominator is just the biggest power, which is 2/3. So in order to get this denominator to be x to the 2/3, we need to multiply this fraction by x to the 1/3 over x to the 1/3. So if we multiplied by x to the 1/3, this denominator would become x to the 2/3, and that's what we need. So then the numerator would also be x to the 1/3. So our combined fraction would be x to the 1/3 plus 1 over x to the 2/3. That's as simplified as we can get. That's where we need to be to figure out our critical numbers. So remember, critical numbers are where this derivative would be 0 or undefined. In the previous problem, the number that made the derivative undefined was not in our domain, so that wasn't a critical number. However, in this case, we get it to work out for us. If x was 0, this denominator would be 0. And if the denominator is 0, this derivative is undefined. If x is 0 in the original function, that's perfectly fine because our domain was all real numbers, and in this case, you would just get 0. So what that tells us is x equals 0 is in fact a critical number. It makes the derivative undefined, but it's okay in the function. That's good. That's what we want. Also, when is this derivative equal to 0? If the derivative is equal to 0, that means the numerator is equal to 0. And we want the cube root of x plus 1 to be 0. That happens when x is negative 1. Because the cube root of negative 1 is still negative 1. We could add this to 1 and get 0 as our numerator. So we got two critical numbers, 0 and negative 1. So let's figure out our increasing and decreasing. So I'll draw a number line with 0 and negative 1 on it. And we're just going to be trying numbers here in the derivative and seeing if we get positive or negative results. The denominator, x to the 2/3, that has an even power because you're squaring. So this is always going to be positive, so we don't really need to check that. If we plug in something less than negative 1, so in this case, since your x values are kind of difficult, you don't just want to pick negative 2 because you might not know what the cube root of negative 2 is. Let's pick something easy like negative 8. The cube root of negative 8 is negative 2. So that would make this numerator negative. Like I said, the denominator is always positive. So we get a negative here. If I plug in something in between 0 and 1, this will be smaller in magnitude. So the plus 1 will make it positive. Again, the denominator is always positive. And if I plug in something positive, then clearly this numerator is positive, positive. So here I have my intervals then of increase and decrease. It's increasing from negative 1 to 0 and 0 to infinity. It's decreasing from negative infinity to negative 1. All right, so I found my intervals of increase and decrease. Next I need to do concavity. So we need to do the second derivative. We need to do the derivative of this. So in this case, we need to do the quotient rule. The 2/3 can just stay multiplied out by the front because that's just a constant. So the derivative of this, again, we're going to use quotient rule. Or actually, you know what? Which will end up being easier is let's just do the derivative of these two terms before we combined it, because that will make the derivative easier, and then we'll just have to combine again, just like we did here. So I'm going to take the derivative of this step right here, since this one's going to be much easier to do the derivative of. Well, this is just x to the negative 1/3 and x to the negative 2/3. That's just power rule. So the derivative of x to the negative 1/3 is negative 1/3 x to the negative 4/3. We subtract the power by 1. The derivative of x to the negative 2/3 is negative 2/3. Subtract the power by 1, you get x to the negative 5/3. Okay, so again, we're going to have to do similar simplification. What can we factor out at first? Well, these both have a negative sign, and they both have a denominator of 3, so we can factor out negative 1/3. That would give us negative 2/9 on the outside. And on the inside, we would get x to the minus 4/3 plus, because we took out the negative, 2x to the negative 5/3. All right, so now we just need to combine them like we did here, and we're good to go. Well, think about what our denominators are. Here they were 1/3 and 2/3, or the x to the 1/3, x to the 2/3. So we just multiplied this one by x to the 1/3 to get it to be a common denominator. What are our denominators here? X to the 4/3 here, x to the 5/3. Again, this only needs an extra 1/3 power to get the denominator to be common. So it's going to actually be the same step as in the first derivative. So our common denominator is x to the 5/3, but we had to multiply this term by x to the 1/3 over x to the 1/3, just like we did here. So now we get x to the 1/3 plus 2. We have a 2 here that we didn't in the previous step. So here's our second derivative. So to find concavity, we're just going to set up a number line with that one. Okay, so again, we're looking at the critical numbers, essentially, of the first derivative to figure out what to put on our number line. What makes this either 0 or undefined? Well, we clearly have 0 on there, because that would make the denominator 0, and that's on the domain of the function. What would make this numerator 0? Well, that's going to have to be that's going to have to be negative 8, because we're solving the equation essentially cube root of x is negative 2. So if cube root of x plus 2 equals 0, cube root of x equals negative 2. If you cube both sides, you get x equals negative 8. So those are our two critical numbers that we're going to put on the number line for the second derivative, 0 and negative 8. Again, all we got to do, plug in numbers to this and see what we get. So this time, we have a negative 2/9 out front, so everything is going to get multiplied by a negative. Also, this time, our denominator is not in even power, so we can't just say it's always positive. We have to check it every time. All right, so let's plug in a number that's less than negative 8, more negative than negative 8. Well, the numerator is going to be negative because this cube root of something bigger than negative 8 is going to be bigger than negative 2 in magnitude. So our numerator would be negative. Our denominator, we're raising to the 5th power and taking the cube root. So if we pick a negative number, that's definitely still negative. So we have a negative numerator, a negative denominator, and a negative constant outside. That would combine to give us a negative result. Let's do something in between 0 and negative 8, like negative 1. Now our numerator is positive because the cube root of negative 1 is negative 1, but we're adding 2. The same logic as before, our denominator is negative because we're only doing odd powers and odd roots. So if it's a negative number, it stays negative. So we have positive numerator, negative denominator, negative constant outside. That gives us a plus. And finally, if we plug in a positive number, numerator is positive, denominator is positive. We have a negative constant outside, so we get minus. All right, so here's our sign chart for the second derivative. Here's our sign chart for the first derivative. You can get your intervals of concavity by looking at this number line. And let's do an approximate graph. Okay, so this is our increasing and decreasing. So let's think about what maxes or mins we might have. Remember, we had no vertical asymptotes, nor no horizontal asymptotes, so I don't need to draw any of those on here. We have a minimum at negative 1. So let's plug in negative 1 to our function and see what that actual point is. Negative 1 to the 2/3 power would be positive 1, because we're squaring it and taking the cube root. Negative 1 to the 1/3 power would be negative 1 times 2. So we get 1 minus 2, which is negative 1. So there's a point on this graph, negative 1, and that is a minimum based off of this. We also have a point at 0 that's a critical number, but it's increasing on both sides. So let's remember what type of 0, I already erased it now, but let's think about what type of critical number 0 was. Remember, this point x equals 0 is perfectly on the domain of the function, but it made our derivative undefined. So if your derivative is undefined, remember that's the slope of the tangent line. So if the slope of the tangent line is undefined, that means we have a vertical tangent line, and it's increasing on both sides of it. If we plug in 0 here, we get 0. So there's a point on the origin, and this has to be a vertical tangent line going through it. We're ready to answer everything else. So we have a minimum here, vertical tangent line here, and let's just figure out what else is going on. So starting from the furthest left that we can, we're always decreasing up to this minimum. So this function is decreasing. But up till negative 8, we're concave down. After that, we're concave up. So let's say negative 8 is out here somewhere. This graph is going to be concave down up until that. Let me make that steeper so that is more obvious. But at this point, it switches to being concave up. So we're concave up, concave down here, concave up after. So this is -8. This is our inflection point. So at -1, we hit a minimum. And we start increasing again, concave up still. But this has to be a vertical tangent line. So it's going to go through this point being vertical. And then what happens after that? Well, it's increasing still, but now it's concave down. So that has to look like that. So how you need to draw this is to make sure that if you were to look at the tangent line at 0, it would be completely vertical. I didn't quite make that a minimum, so let me fix this. So then we have a minimum here. So this is basically what this graph would look like. You have a vertical tangent line that goes to the origin. You have a minimum at -1, -1, and we have the correct ways of increasing, decreasing, and concavity otherwise.
The Teaching Center, UF's Learning Resource Center.